Hey everybody, my name is Chris and I'm a tutor here at Chegg.com. I mostly do math and a little bit of computer science, and in this video we're going to do an example of using the residue theorem. So here we want to evaluate the integral over c of 1 over z squared plus 1 dz, where c is the circle, the modulus of z is less than 4. So essentially this is the circle in the complex plane that's centered at the origin and has radius 4. Okay, so we're looking at the interior of that circle. So we want to use the residue theorem to evaluate this integral. So how are we going to do that? Well, the residue theorem says that what we can do is take the integral over c of 1 over z squared plus 1 dz, and that's going to be equal to 2 pi I times the sum of the residues. So actually, let's say j, we use j as the index variable, times the sum of the residues. And as it turns out, this actually only has 2 residues. So from j equals 1 to 2 of the residues of 1 over z squared plus 1 evaluated at z sub j, where z sub j basically, j ranges from 1 to 2, so z sub 1 and z sub 2 are the residues, or sorry, the poles, z sub 1 and z sub 2 are the poles of this function here inside of c. Right? And where are those? Well, those are, well, first of all, in the complex plane we can say z squared plus 1 equals z plus I times z minus I. So this equals 0 when z equals I or minus I. Okay? So these are the zeros of the denominator, which means I and minus I are the poles of this entire thing here. So z sub 1 and z sub 2 are I and minus I. It doesn't matter which one's which, as long as we account for both of them. So let's go ahead and do this then. So using the residue theorem, we have the integral over c of 1 over z squared plus 1 dz equals 2 pi I times the residue of 1 over z squared plus 1 at I plus the residue of 1 over z squared plus 1 at minus I. All right, now let's go ahead and calculate these residues separately so we don't have a bunch of clutter up here. That's an I right here. Okay, now we know we can use the residue theorem because this everything here, the hypotheses are all satisfied. So the hypotheses basically say that this function here has to be analytic on c and the boundary of c, which would be z equals 4. So everything's totally fine there. It has to be analytic on the boundary of c and the interior of c, except possibly at finitely many points. And that's exactly what's happening here. There are 2 points inside c where this is not analytic, and it's precisely these poles, I and minus I. So we know that we can use the residue theorem. So let's go ahead and calculate the residues now. So the residue of 1 over z squared plus 1 evaluated at I is equal to the limit as z approaches I of, now to do the residue theorem here, to actually calculate this, it'd be more helpful to factor. So I'll write this as in the factored form. And then we're going to multiply by z minus I because we're taking the limit as z goes to I. So this is how we calculate residues. So z minus I, those cancel. So really all we have is the limit as z approaches I of 1 over z plus I, which is 1, oops, getting ahead of myself a little bit, which is 1 over I plus I, which is 1 over 2I. All right? So that's this residue right here. It's equal to 1 over 2I. Now how about the second residue? That's going to be the residue, oops, of 1 over z squared plus 1 evaluated at minus I, and that's going to be the limit as z approaches minus I of, so same thing, we're going to use the factored form, and now we're going to multiply by z plus I because of that's what the residue formula tells us to do, and cancel, cancel, that's great. So we're left with the limit as z approaches minus I of 1 over z minus I. So as z approaches minus I, this becomes 1 over minus I, which is 1 over minus 2I, or in other words, minus 1 over 2I. Okay, now if we go back to here, so then what we have is this integral over c, 1 over z squared plus 1 dz is equal to 2 pi I times the sum of the residues, but what we see is that, remember, the first residue was 1 over 2i, and then plus the second residue, which was minus 1 over 2i. Well, the sum of the residues is actually just 0, so the entire thing is just 0, okay? So that's what we have going on there. And this has been an example of using the residue theorem to evaluate a complex integral. I hope you found this video helpful, and thank you for watching.